Imagine you want to predict the path of this bouncing ball. If I want to predict where it's going next, physics tells me to write a differential equation, something that explains how its position changes from one instant to the next. Machine learning works differently. We give a neural network a stack of layers and let it learn a pattern from the data. But what if we could combine the two concepts? That's the idea behind neural ordinary differential equations, or neural ODEs, a hybrid of math and AI that lets us model change continuously in time, as if the network itself obeyed a differential equation. Traditional neural networks are like climbing a staircase. Input goes through one layer, then the next, until we reach an output. And this works well for images or text, where data is naturally structured in layers. But many processes in the real world, like population growth, chemical reactions, or the motion of planets, don't happen in discrete steps. They evolve continuously. And neural ODEs let us treat the network itself as a continuous process, learning the underlying rules of change over time. At the core, a neural ODE is just a differential equation, where the derivative of a hidden state z with respect to time t is defined by a neural network. Here, in this case, f is a small neural network that outputs how z changes at any moment. Then, just like in calculus, we use an ODE solver to calculate z at any future time. You can think of it like following the slope of a hill at every tiny step, rather than just jumping from step to step. One key trick that makes neural ODEs so practical is the adjoint method. It lets us compute gradients efficiently, so we can train the network on data just like backpropagation in a normal neural network. In other words, neural ODEs combine the elegance of calculus with the power of machine learning. Neural ODEs shine in any scenario where change is continuous. For example, physicists might use them to simulate complex dynamical systems like planetary orbits or fluid flow. Economists might model stock prices as a smooth process over time. Epidemiologists can use them to predict disease spread more accurately, especially when data is sparse. Even in computer vision, neural ODEs can generate intermediate frames in videos, producing smoother transitions than traditional models. What excites me the most about neural ODEs is that they bridge the gap between continuous mathematics and machine learning. They remind us that the universe is continuous, not just discrete blocks of data. By learning the rules of change directly, neural ODEs let us build models that are smoother, more interpretable, and often more accurate. It's like giving neural networks the power of calculus. So, if you want to dive deeper into neural ordinary differential equations, here are some great starting points and the resources that I used when making this video. Thank you so much for watching.